This is the story of execute in place on ARM64. We booted a mainline Linux kernel directly from flash memory. It runs in just over 1 megabyte of RAM. To understand the problem, it helps to see how an ordinary ARM64 kernel boots. Normally, a bootloader copies the whole kernel image into RAM and jumps to it. Early assembly code sets up initial page tables. It turns on the memory management unit. The kernel then builds its real page tables. It initializes memory. It mounts a root file system. Then it runs the first user space process. That process is called init. Throughout all of this, the kernel is assumed to be one contiguous writable image in RAM. Execute in place breaks that assumption. The idea is simple. Leave the kernel's code in flash and run it directly. It never occupies RAM at all. This matters for deeply embedded devices. They have plenty of cheap flash, but only a tiny amount of RAM. ARM32 and RISC-V have supported this for years. ARM64 did not. The first problem is fundamental. ARM64 patches its own machine code at boot time. It swaps in faster atomic instructions. It applies errata and security workarounds. This all happens through the alternatives framework, but code in read-only flash cannot be rewritten, so the most performance-critical mechanism on ARM64 simply cannot run. The second problem is that the kernel image is now torn in two. Its code and read-only data sit in flash at one physical address. Its writable data and page tables must sit in RAM at a completely different address. Almost every piece of early boot code assumes a single contiguous image. Every one of those assumptions has to be unwound. With the problems understood, here is how each one was solved. And here are the new problems we found along the way. The solution to the first problem is to run with patching switched off. Instead of patching branches into the code, the kernel records CPU capabilities in a bitmap. It then consults that bitmap at runtime. This mirrors how ARM32 and RISC-V handle their own execute-in-place builds. For the split image, a new linker script places code in flash and data in RAM. It also records where the master copy of the data resides. Then, in the very first assembly instructions, the writable data is copied out of flash into RAM. This happens before any data is touched with the memory management unit still off. Because the image now spans two physical regions, the address translation helpers are made region-aware. The early identity map gains three mappings. The first is the flash code. The second is the RAM data. The third is an alias. That alias lets position-independent code reach its data before the real page tables exist. Along the way, new problems surfaced. When QEMU boots this configuration from flash, it does not hand the kernel a device tree pointer. The kernel has to find it by scanning RAM for the device tree magic number. Worse still, early debug output was overwriting that very device tree. That bug took real detective work to find. Another failure was more subtle. The kernel gives user space a small shared library called the VDSO. It normally resides in RAM. In flash, it has no memory backing, so an early attempt simply skipped it. But without it, the signal return path pointed at unmapped memory. The kernel then panicked the instant any program received a signal. The fix is to copy the VDSO into a single RAM page. 4 kilobytes well spent. With the kernel booting, the last task was to make it fit. Multiprocessing was made optional. The flat memory model replaced the sparse one. Heavyweight subsystems were removed. The allocators were tuned for a system with barely a megabyte. The root file system's decompression buffer was deferred, so it is never allocated. Step by step, the footprint fell from 4 megabytes to just over 1. The result is a mainline ARM64 kernel that boots to an interactive shell. It needs just 1152 kilobytes of RAM. The 1.2 megabyte kernel runs entirely from flash. Not a single byte of kernel code sits in RAM. None of this comes for free. To reach 1 megabyte, we accept a stark set of limitations. The system runs on a single CPU core. There is no multi-threading. Every speculation and security mitigation is switched off. There is no networking. The only input or output is a single serial port. So this is not a general-purpose kernel. It is the right tool for a closed, deeply embedded device. One that runs trusted code. One that takes no untrusted input. One that runs on emulated or verified silicon. Within those bounds, it is a genuine working Linux system in about 1 megabyte. The work is complete. It is packaged as 2 clean patch series against mainline version 6.19. It is ready for upstream. It is ready for upstream.